Dear students, in the previous session we have discussed principle of superposition and classification of second order linear partial differential equations into hyperbolic, parabolic and elliptic PDEs. So now let us solve some problems using the canonical form method. The first problem is determine the nature of the following PDE. That means we have to find out whether the given PDE is parabolic, elliptic or hyperbolic. So we have a standard equation, that is second order linear PDE. Using that second order linear PDE, we have to find out the nature of the given partial differential equation. So for that we need to compare our given equation into this second order linear partial differential equations. Then we have to find out the discriminant, that is nothing but b square minus 4ac. If the value is greater than b square greater than 0, it will be hyperbolic. If the value is equal to 0, it will be parabolic, and if the value is less than 0, then the given PDE is elliptic. So let's solve the problem. The first problem is dou square z by dou x square is equal to x square dou square z by dou y square. So I can write that equation as dou square z by dou x square minus x square into dou square z by dou y square. All I have done is I have taken my right hand side to the left hand side. So the positive sign becomes the negative sign, which is equal to 0. So now this is my second order PDE, which is in general form. I am comparing my given PDE with this second order PDE. So if I compare with this, zxx is nothing but dou square z by dou x square. So the value of a, that is dou square z by dou x square's coefficient is a. A is 1. Dou square z by dou x into dou y, that is not there in my given equation. So the coefficient of that will be 0. Next, dou square z by dou y square. I have dou square z by dou y square. Its coefficient is minus x square, because the general equation consists of positive sign. Here it is a negative sign. So the coefficient of dou square z by dou y square will be minus x square, and there is no d, e, f and g terms. That is nothing but there is no partial differentiation of x, y or a function x comma y. So I am writing it as d is equal to e is equal to f is equal to g is equal to 0. So now I have a, b, c. Using these values, let's find out the discriminant, b square minus 4ac. Since b is 0, it is 0 minus 4 as it is, a is 1 and c is minus x square. So minus into minus, it will be plus 4x square. So if I give any positive value to x, 4x square will be obviously greater than 0. So from our condition that if b square minus 4ac is greater than 0, then the given PDE is hyperbolic. The next problem is dou square z by dou x square plus 2 into dou square z by dou x dou y plus dou square z by dou y square is equal to 0. Again compare this with the general second order PDE. So if I compare, I will get the coefficients for dou square z by dou x square as 1 and dou square z by dou x dou y is 2. Dou square z by dou y square is c that is 1. So other than these three terms, all are 0, because there is no dou z by dou x, dou z by dou y, z. So d, e, f and g will be 0. Again let's check for discriminant, that is b square minus 4ac. B square means b is 2, so 2 square is 4 minus 4 as it is, a is 1, c is 1, so 4 minus 4 it is 0. Therefore the nature of the given PDE is parabolic. Similarly, the third problem is 3 into dou square z by dou x square plus 2 into dou square z by dou x dou y plus 5 into dou square z by dou y square plus x into dou z by dou y. So check carefully. Here I have e term also. I don't have d but I have e, that is I don't have dou z by dou x in my given PDE, but I have dou z by dou y. So if I compare with the general second order PDE, I will get values as A is equal to 3, B is equal to 2, C is equal to 5, D is 0 and E is x, F, G will be 0. So again let's check for discriminant, that is B square minus 4AC. So 4 minus 4 into 3 into 5, 4 minus 60, 5 3s are 15, 15 4s are it is 60. 4 minus 60 is minus 56, which is less than 0. So the nature of the given PDE is elliptic. The next problem is, show that the equation dou square z by dou x square plus 2x dou square z by dou x dou y plus 1 minus y square into dou square z by dou y square is equal to 0. This will become elliptic when x is inside the region, that is x square plus y square is less than 1. And this the nature of this PDE will be parabolic when x is on the boundary, that is x square plus y square is equal to 1. On the boundary means x square plus y square is equal to 1. So if I consider one circle, if I say inside this region means I can take the value like this. If I say on the boundary, it will be exactly on the cutting axis. If I say outside the boundary, it will be like this. So they have given that we have to show that the given PDE is elliptic if the region is inside the x. It will be parabolic if it is on the boundary and hyperbolic for outside the region. So let's solve this. This is the given PDE. I am comparing this given PDE with standard second order general PDE. So if I compare this with that general PDE, I will get A is equal to 1, B is equal to 2x and C is equal to 1 minus y square. So this is the discriminant with which I should check whether the given PDE is elliptic, parabolic or hyperbolic. So now I have B is equal to 2x. So 2x whole square minus 4 into 1 minus y square. It will be 4x square minus 4 into 1 minus y square. That is nothing but 4x square minus 4y square. Sorry, minus into minus it is plus 4y square minus 4. So if I take 4 as common, it will be x square plus y square minus 1. So now let's check for the condition. If given equation is elliptic, then it must be b square minus 4ac should be less than 0. So this is my b square minus 4ac. My b square minus 4ac value is 4 into x square plus y square minus 1. This will be elliptic if 4 into x square plus y square minus 1 is less than 0. Isn't it? So I can rewrite this as x square plus y square minus 1 will be less than 0. This is nothing but x square plus y square will be less than 1. So I have proved that b square, this given PDE will be elliptic if x square plus y square is less than 1. That is nothing but when x takes the value of inside the region. Inside the region. Okay, this is the b square minus 4ac value. Let's check for parabolic now. 4 into x square plus y square minus 1. For parabolic, b square minus 4ac will be equal to 0. So this I will take it as this is equal to 0. So this will be x square plus y square minus 1 is equal to 0. So x square plus y square is equal to 1. That is on the boundary. On the boundary. Okay. So the last condition is hyperbolic. That is b square minus 4ac should be greater than 0. So again 4 into x square plus y square minus 1 is greater than 0. This implies x square plus y square minus 1 is greater than 0. This is nothing but x square plus y square is greater than 1. That is outside the boundary. The next problem is we have to transform this PDE into its canonical form. That is, first we have to find out whether the given PDE is hyperbolic or parabolic or elliptic. After that, we have to transform this given PDE into its canonical form. We have seen the three nature of the PDEs and corresponding canonical form. So, once we get to know that whether the given equation, the nature of the given PDE, then we can easily convert that to its canonical form. In the previous session, I have told you that if in my general second order PDE, if A, B, C, D, E, F and G takes the value of constants like A is equal to 1, B is equal to 2, C is equal to 3, like that, if it takes the constant values, then that PDE is called as second order linear PDE with constant coefficient. If any of these A, B, C, D, E, F or G is a function of X or Y, then that particular PDE will be called as second order linear PDE with variable coefficients. In general, this classification of second order linear PDE will be measure of variable coefficient problems. We won't get, most of the time we won't get the constant coefficient problems. And also for constant coefficient problems, we can solve using another methods also. But for variable, this is one of the easiest way to solve the given PDE. So for example purpose, I have taken one constant coefficient second order linear PDE. So transform the equation uxx plus 2uxy plus 4uyy plus 2ux plus 3uy is equal to 0. I have to transform this to its canonical form. So first step is we have to compare this given PDE with our second order PDE, that is the standard equation, that is auxx plus buxy plus cuyy plus dux plus euy plus fu is equal to g. So if I compare my given PDE with this standard PDE, I will get A is equal to 1, B is equal to 2, C is equal to 4, D is equal to 2, E is equal to 3 and F and G will be 0. So now I have to find out the discriminant in order to know the nature of the given PDE. So let's find out the discriminant, that is b square minus 4ac is equal to 4 minus, that is b is equal to 2. So 2 square is 4 minus 4 into 1 into c is 4. So 4 4s are 16, 4 minus 16 is minus 12, which is less than 0. So the nature of the given PDE is elliptic. So till here the method we can solve the we can solve this problem in two ways. But in both the ways, till here the methods follows the same. The next part will be different. So what I have done here is, this is the characteristic equation for elliptic, that is dy by dx is equal to b plus or minus square root of b square minus 4ac by 2a. So dy by dx as it is, b is 2 plus or minus square root of 4 minus 16 by 2. So if I simplify this, I will get 1 plus or minus I root 3. That means my dy by dx takes two values. One is 1 plus I into root 3. Another is 1 minus I into root 3. So let's integrate this with respect to x. So I will get y is equal to 1 plus I into root 3 into x plus c1. And another will be y is equal to 1 minus I into root 3 into x plus c2. So if I write this for c1, c1 is equal to 1 y minus 1 plus I root 3 into x. c2 will be y minus 1 minus I into root 3 into x. In the last session, I have told you that the transformation of independent variables x and y, it will change to new variable, that is xi and eta, isn't it? So my c1 will be xi of x comma y, that is the transformation taking place, and c2 will be my eta of x comma y. So this is the new coordinates or new transformation from x and y to xi and eta. So I have written it here. The new coordinates or xi of x comma y is y minus 1 plus I root 3 into x, and eta of x comma y will be y minus 1 minus I root 3 into x. Since it is elliptic, there is a conjugate term. In order to remove this conjugate term, we will introduce one more transformation, that is xi and eta plane to alpha and beta plane. So for that transformation, I will define alpha as xi plus eta by 2 and beta as xi minus eta by 2i. So if I solve for alpha, I will just substituting the value of xi and eta by 2 as it is. So these two terms gets cancelled. I will get y minus x. Similarly for beta, I will get minus root 3x. So now initially it was xy coordinate. It then changes to xi and eta coordinate. Since the given PDE's nature is elliptic, in my xi and eta plane there is a conjugate. The existence of conjugate makes you to consider one more transformation, that is alpha and beta. So now this is the canonical form for elliptic. Okay, so see, there is a bar, b bar, c bar, d bar, e bar, f bar as well as g bar. Since no terms become 0 in this nature. In the derivation part, we have seen the value of a bar, b bar, c bar, d bar, e bar, f bar, g bar. So this is for xi and eta plane. Now our new plane is, that is new coordinate is alpha and beta. So that eta plane is converted to alpha and xi plane is converted to alpha and eta plane is converted to beta. So in the place of xi, I have written alpha, and in the place of eta, I am using beta now. So the same a bar, b bar, c bar, d bar and e bar, f bar, g bar values will be in terms of alpha and beta now. So a bar is equal to a alpha x square plus b alpha x alpha y plus c alpha y square. Now I have the value of alpha, so I can find out alpha x and alpha y, that is differentiation of alpha with respect to x and differentiation of alpha with respect to y. Similarly for beta, I can find beta differentiation of beta with respect to x. Since there is no y term, differentiation of beta with respect to y will be 0. So here alpha x, that is differentiation of alpha with respect to x. Since alpha is equal to y minus x, if I differentiate this with respect to x, I will get minus 1. Minus 1 whole square, it is plus 1. So alpha x, again it is minus 1. Alpha y, it is 1. So alpha y, that is differentiation of alpha with respect to y, it is 1. So substituting all the values, you will get a bar as 3. Next b bar, that is 2a beta x alpha x plus b into beta x alpha y plus alpha x beta y plus 2c into alpha y beta y. Since beta is minus root 3 into x, beta with differentiation of beta with respect to x, it will be minus root 3. Okay. So I am just substituting all the values and I am finding out b bar value. It is 0. Similarly for c bar, d bar, e bar, since there is no f terms, f bar will be 0 and there is no g bar, g is 0, so g bar is also 0. Now I have to substitute b, c, d, e, f, g, h in my canonical form equation. Okay, canonical form equation is this. So I am substituting all the values in this equation. So a bar is 3, b bar is 0, c bar is 3, d bar is 1, e bar is minus 2 root 3, f bar is 0 and g bar is 0. So if I substitute all the values, I will get 3u alpha alpha plus 3u beta beta plus u alpha minus 2 root 3 u beta. This is the transformed equation, that is for my given PDE. This is the transformed equation, which is nothing but canonical form. The next problem is I have to transform this given equation into its canonical form. So I have told you that if any of a, b, c, d, e, f or g is a function of x or y, then the given PDE is called as second order linear PDE with variable coefficient. So you can see here sin square x, sin 2x, cos square x and here also x. So this is the example for second order linear PDE with variable coefficient. So let's compare this given PDE with my standard equation. I will get a as sin square x, b as sin 2x, c as cos square x, g as x, e, d, f will be 0. So let's find out the discriminant. Sin 2x whole square, that is b square, minus 4 into a square is sin square x into c is cos square x. So b square minus 4ac. Sin 2x is nothing but, general formula for sin 2x is 2 sin x into cos x. I'm just substituted here. So 2 sin x cos x whole square minus 4 sin square x cos square x. This is nothing but 2 square is 4, sin square x cos square x. So plus minus gets cancelled. I will get b square minus 4ac as 0. So the nature of the given PDE is parabolic. For parabolic, this is the canonical form and the characteristic equation. In general, we will consider the characteristic equation as dy by dx is equal to b plus or minus square root of b square minus 4ac by 2a. Okay, in the case of hyperbolic and elliptic, this term will retain as it is. This will take either the value of positive or negative. If it takes negative value, it will be in the form of imaginary or conjugate terms. Then we will call the nature of the PDE as elliptic. If it takes the positive value, then obviously it will be hyperbolic. In the case of parabolic, b square minus 4ac takes the values